Thank you very much for the invitation to be here, and it's always really great to participate in the party for Sergio's birthday. There's been few, Sergio. Now the next, we wait 5 more years and then we'll do it again.
85.
Yeah, well, no, 80 and then 85 and then we go by 5. So anyway, this is in the topic of fluids and water and the waves and singularity and so on. So in particular, actually this is the first time I present this talk, and my former student Riccardo Grande gave, actually also Alberto Maspero has given us talk on this thing, and I have to say that in particular among all of us, Riccardo is the one that learned probability. The idea of working on this problem came when we just started the collaboration in wave turbulence supported by the Simon Foundation. This was almost 6 years ago now. And one recommendation, or one thing we promised we were going to do, thanks to the support of the Simon Foundation, was to interact with physicists, experimentalists, and so on. So when Eric van der Heijden from Courant gave a talk in the first meeting that we had, I was thinking, well, maybe we can try to turn into some rigorous mathematics what Eric and his collaborators in this paper had done most in a numerical manner. And so what's the topic? So the topic is understanding the probability of formation of rogue waves. And rogue waves were considered to be just some fantastical things that the sailors will talk about just to impress people. But it turned out that we can actually observe them now, also in particular via satellites, but also in a very small environment, such as here. This is in a tank. And what is a rogue waves? Well, just imagine that from the basic equilibrium state of the water, you consider to be a rogue wave, a wave which is twice as large the average that you have around it. So just to make this problem into mathematical setting, imagine that, okay, this is the tank and this is the ocean. I'm going to just consider a slice of either the tank or the ocean, so that then I will just record what the profile does. So basically this is, just for you, this red part corresponds to this red part. It's going to be periodic, and my notation eta tx is going to represent the free surface on the top. By the way, Alex did a wonderful presentation of the general problem of water waves. So he reminded us of who were the people who have worked on this. Most of his presentation was when the domain is actually either R or R2 or N. In this case, we are periodic, and much less has been done in there. Now, there are 2 theories and 1 conjecture that I want to make in terms of the probability of finding rogue waves. The first theory, so this, by the way, these 2 pictures came from Quanta magazine, and here the first theory is called the linear addition, but in our paper actually we use the word dispersive focusing, but it's the same thing. And it says the following: the idea is that a rogue wave will form when there is interactions of these wave groups that are basically linear. So for example, see here the light purple, then the deep purple, the blue, and then when they conspire together somehow, and we'll see later, you end up having something which is at least twice as big as the average of the rest. So this is basically dispersive focusing. It's something that comes more from something linear and then combines together. The second theory instead is nonlinear focusing. And well, you see here the pictures is now this purple, light purple and so on. They are not nicely like the one above. So that's supposed to tell you that you're talking about something nonlinear coming together. So these are the 2 different theories from physics, and the conjecture is that if you start with the profile which is, so this is time zero, follows Gaussian distribution, zero mean and sigma deviation here, then the probability that the height of my wave, so the sup in x, so the highest part of my wave is bigger than h0. H0 is a positive constant. It goes like exponential to the minus h0 square and then normalized by sigma. So that's...
Zaharoff made another conjecture that there is a soliton.
Yes, but here we are not talking about solitons. This is not something that comes from solitons. Yes. In fact, doesn't maintain. One of the things is that when the wave peaks, but then doesn't move just like we are thinking in solitons. Okay, so I'm going to start with the main result, and then I'll try to guide you towards the proof of this. So the main result is the following. This is in collaboration with Berti, my former student Grande, Maspero, and myself. So we fixed the domain tau, which is just the circle 0 to pi, and eta tx is the free water wave surface on the top. And we start with smooth random initial data, eta omega 0x, distribute as a Gaussian random variable, zero average and standard deviation sigma that I talked about before, and this is going to be small. Now, when h, this constant h, which basically measures, if you want, what happens at time zero, and how much bigger that is, h, which is much bigger by sigma, but still small, and any time t, h to the minus 3, actually this minus 3 will be recurrent. You will see why minus 3 is important. Then the probability is this, exactly what was expected. Now, this theorem is for small data, or small data regime. In fact, let me give you a little bit of remarks on that. So the condition h0 to be much smaller, much smaller than 1, corresponds to the weakly nonlinear regime of the water wave dynamics. But note that here the period is very small. So if you are really looking at a very large body of water, then by rescaling the problem, you can think that what we are observing are really wave of a certain not trivial height, but in a very large body of water. So we recover that. It's not just a small problem in that sense. It's all rescaling that will give you that. Now the time interval less than h0 to the minus 3, so h0, think of it to be the initial data if you want, is in a sense optimal because minus 3 is exactly the time length of existence of a small solution for the water wave problem in the periodic setting. And in fact, it might happen that after this time, there are the quintic resonant part will come in and might, in fact, lead to much more instability and will be much harder or maybe impossible to understand this problem after this time, h to the minus 3. Now, what's the main difficulty in doing this? Well, the difficulty is in the fact that although you can start with something which is Gaussian and you understand very well, in general the surface profiles eta tx, a later time, in particular close to this length of time here, does not necessarily remain Gaussian. Okay, so we cannot expect that happens. And this is not expected because the very highly nonlinear interaction that we have in this problem. This is quasi-linear problem. And hence that makes if you want to do a large deviation principle and something that you don't know how really behaved after longer time like that, then what do we do? So now,
so your hypothesis expressed just in terms of the surface, just in terms of eta being random, you don't do anything about the velocity potential?
No, so only eta. Well, no, okay. Eta, let me write this, and then when I state the problem, basically from when there is a xi and there is an eta, you have to do conditions in both of them. Yeah, you will see when I'll state it a little bit more precisely. So I want to give you a gentle sort of introduction to the proof of this theorem. And for that reason, we're going to start with the linear Schrödinger equation. Okay, and that will give us a little bit of an idea what are the tools that we can use. Now, of course, this is linear, so you know exactly what the evolution is, but that will tell you, will give you a little bit of information on what we can do. Right, so this is the linear Schrödinger, again, one dimension. At time 0, the initial data use 0 omega, and it is of this type. So it's very smooth, but it's random. In what sense is very smooth? Well, because this CK are just very fast decaying objects. In fact, decay like e to the minus bk, where b is a positive number. Eta k is complex the Gaussian standard variables in a probability space I'm going to call omega. And then there is the epsilon here that tells you that I'm working in a small data problem. And the theorem, which is not such a big deal, and I will show you how you prove it. This is with, it's the first work that we did in this problem. And Grandel, as I say, at that time was my former graduate student, as well as Kuryansky. She did the numerical part of this work, and Garrido was a graduate student in probability. We definitely needed him at Columbia at that time. And this is exactly rewritten in a slightly different way. It's exactly the same kind of theorem that I stated before, but of course now for the linear solution. So the log of the probability of the sup of the wave, the magnitude of the wave, greater than z, 0, epsilon 1 minus delta, it behaves like that. So it's renormalized in a way so it becomes so very nice at the end, the way you see it. Now, proving this theorem is not very hard, so we're going to go through that. By the way, a little disclaimer, I'm not at all a probabilist, so anything which is purely probability here doesn't come from me, and if you notice a mistake with it, it's probably a typo, and I'm not going to be responsible for that. Okay, so as I said, this is a linear problem, so we know exactly how evolves the initial data. In fact, the only difference between my initial data and what happens at any time t later on is e to the I minus t k squared. All right, so that's because of the Schrödinger. Now, the upper bounds for this kind of problem is always pretty easy to do, and basically the mechanism is always the same. And by the way, in order to believe this kind of inequality, you have to be a little bit of a gymnastics with your head, because here is greater or equal than, here is less or equal than, so you have to include the sets in the right way. But believe me, this is the way it goes. So the probability of this event happening is less or equal to the probability when you put absolute value everywhere. Bigger than z, I rescale the epsilon in the right way. And now, for this upper bound, there is a theorem that is used. And the theorem is the Gardner-Ellis theorem, which is some kind of central limit theorem that says the following. Now, if I'm looking at this event here, and I look at I'm going to call it z epsilon, because it depends on epsilon, the probability that z epsilon is greater than z0 is less or equal than this quantity, well, the infill lambda greater than 0. This follows from the way this theorem is stated. And then here, when you have the expectation of these parts, that becomes the product, and then you just compute, and there it pops the right number. So the upper bound is never a problem. You do less or equal than, you apply this, and it's okay. And this is going to be actually pretty stable also when you do the nonlinear problem. It's pretty, it's a good rigorous thing that we can do also later on for nonlinear problem. But now what about the lower bound? That's harder, because in the lower bound, you have to tell me that there are objects that actually behave in the way I want them to behave. So this is a harder thing to prove. So let's see what we can do in this linear part. So now the probability that the sup is greater than that is greater or equal than the probability that evaluating the solution at x equals 0, for example, or any other point on the line, is greater than z epsilon to 1 minus delta. Now I know exactly how this looks when I set x equals 0. Now this is only depending on k. And if you take the absolute value of this quantity, this is a Rayleigh distribution, and you write it down, and there it pops. So this is very simple, because there is no, when you set this x equals 0, there is nothing here that it comes from the nonlinearity. So it's very simple, assuming that you know the probability of these facts, that you have this particular quantity, that they have a certain distribution, and so on. But this is not a very robust argument. It's not going to work when you have nonlinear problem. So we had to do something a little bit more robust. And this is the way we're going to proceed. So we need a more robust strategy, because if we wanted to do something for the lower bound, for the nonlinearity, what I just did is not going to fly. So let's assume now that we write a random, this is the random variable, my initial data random variable. I'm going to write in polar coordinates. So the magnitude and the phase. And then I'm rewriting again. This is a linear solution. I'm going to just rewrite that way. By the way, this CK, you can think of them to be already positive to start with. And then here is my phase that comes from my initial data. And here is the fact that I have a linear Schrödinger equation. This is the reconstruction via Fourier transform. Now, remember that before I knew how to understand probability if my event is of this type. In fact, for the upper bound, we took absolute value and we were fine. But I would like to do something like that from the lower bound. And when is this actually happening? This is happening when there is a perfect, for example, very nice alignment of this, this frequency here, of this phases here. So if we if we can say that the probability that this phase get all aligned, then my solution is going to look very much like that, right? Because e to the I 0 is going to be 1, basically. So I'm looking at the set such that these phases are going to be less than epsilon. So this quantity here is basically 1. So basically my solution is of this type, for which I know very well what the distribution is. So the question, not just in this case, but also when we address the nonlinear problem, is going to be try to understand that the set in which my phases are going to be aligned is exactly the set, or the same measure of what the upper bound gives me. And so then I have an upper bound and a lower bound. And this is the hard part of the problem. Figuring out when do we have, or if we do have, this alignment of phases. All right, so let's do a little bit of calculation. Let's call dtx to be exactly the set I want to measure, the omega such that the sup is greater than z0, epsilon 1 minus delta. And A be the set of omega in which I have this basically perfect alignment of all my phases. Of course, I don't expect this for all k, so I'm going to say that this is less or equal than a certain number of frequency, n epsilon. And n epsilon will be taken large enough in terms of epsilon. Now, the probability that this happens is basically of this order. So when I do the probability of this element, of this event, which is the one I want to measure, this is going to be bigger or equal than the probability when I intersect with this. But when I intersect, all my phases are basically almost aligned. So then my solution looks very much like this. So then I measure this probability, which I did already for you for the upper bound. And I multiply by this probability, they are independent here. And then what I lose here is going to be exactly this quantity. And if n is large enough, so that can be, this is the most important piece. In particular, n epsilon log epsilon is going to be less than that. Then I will be done. Okay, so in this example, which just was the linear problem, I discovered that I have a method, which is that of aligning the phases, that might actually be robust enough also when I consider the nonlinear problem. So let me tell you what happens now for the cubic NLS. Now, I should remind you that the cubic NLS 1D is actually an integrable system. But there is no integrability here. And the kind of argument that I'm going to present is not going to be just for the cubic nonlinearity. One can actually do it more in general. So I just want to make sure that it's clear that whatever I'm going to do here is not using integrability at all. So now, again, just like, yes.
Depends on dimension, right? Integrability.
This is 1D.
So everything is 1D, okay.
All of this is 1D. A good question that maybe somebody would have asked at the end, but I'm preemptively going to answer, is the wave, the water wave system that we are going to do here, we're going to use here, just like the case that Alex talked about last time. It's 1D, like you slice your body of water and you just see what happens there. One can ask what happens in the 2D. And that's much harder, and it's not done yet. Okay.
But you have a conjecture, of course.
Yes, we do have a conjecture, which should be the same as this, but it's much more complicated. Okay, so now let's go to the nonlinear Schrödinger, because what I showed you before was the linear. Same initial data, the ck fast decaying, the eta k are going to be random. And the theorem that we proved, in fact, is exactly what you expect. This is the large deviation principle for this problem. But now in this case, it's not for all times, like it was the case for the linear NLS, because it really didn't matter where we were for the linear NLS. This is for the time epsilon to the minus 3, and this is the 1 minus delta was the size of the initial data somehow. Okay, so can we go further in time? That's a question that Ricardo is addressing. And let me tell you what's the strategy now. So first is, well, we have to find some kind of approximation of our nonlinear solution on which I can use the kind of tools that I show you for the linear one. And then for this approximated solution, I want to prove that there are good tail distribution, exactly the large deviation principle. So what is the approximation that I'm going to use? Let's see. Now, well, as I mentioned already before, the upper bound is not really a problem, because if you remember, what we did was to look at the solution, put the absolute value everywhere, and you're good. So I'm not going to say much about that, because it really works like the linear case. The lower bound is really what's complicated, but you have to tell me that there is a bunch of waves that are going to grow. So that's what I will concentrate on. So the first attempt that we did in order to solve this problem, in understanding what is the approximate solution that is going to basically follow my real solution, but for which I can do some probability on it, is the solution of the NLS, in which instead of taking all the 4-wave interactions and the nonlinearity, all of them, I'm concentrating only on the resonant ones. This is kind of an intuitive thing to do at the beginning, because if you expect something to grow, in this case it's some kind of L infinity growth, you expect that that comes from the resonancy. So you take your 1D cubic NLS, you assume that the frequency are interacting only in a resonant manner, and then believe me on this, that's how you can write the solution of that system. So this is not the whole solution, it's only of the part that resonates. And I'm going to call this U approximate. And like I said, believe me that this is the way it's going to go. Now, this part is really not important, because when you take the absolute value, this disappears. So the only part that's going to be important for us to analyze is this. And in here, you see this is the Schrödinger like in the linear case. This is just reconstructing. And this is basically what looking at the resonant part does to my amplitude. And I already learned from the linear part that in order to obtain the lower bound, I have to look for phase alignment. Now, what's the phase? Well, this comes from, if you remember, this comes from the phase of the initial data that's going to be there. And then this is the effect that comes from taking the nonlinear resonant part. And here, just for you, because I'm going to look at this in a little bit, what is this part? This, if you write it down, this is nothing else than the Fourier coefficient at time 0 square times t. Okay. And so I'm looking again, when do they align and what is the measure of that set? And by doing that, and just how I showed you before, well, we can, yes, move forward, but only for epsilon to the minus 2. Okay, we don't reach epsilon to the minus 3. That approximate solution was not good enough. So the second attempt was to substitute this, which was the size of the Fourier coefficient at time 0 square, which now the integral between 0 and t, the Fourier coefficient from 0 to t. This average is much more efficient because it also takes care of things that happen at time 0. And I'm not going to do the argument for you, but by using this new approximate solution, we obtain a better result. In fact, we can go all the way to minus 3. Okay, so now we are going to the waterway problem. And now the question of Alex, what are my initial data precisely, is going to be fully stated. So as Alex did prepare us already in his work, in his talk, the setup is the following. So we're going to be in the regime in which there is only gravity. The body of water is infinite depth. So this is my way of indicating that. Eta Tx, as I say, is just the basically the curve between, if you want, air and water. And you can write this, and I'm not going to spend much time because it's not going to be very informative. You can write the system by also involving, in a sense, the Dirichlet normal operator. And Alex talks a lot about this, so there is a very precise system that you can write. And I'm going to also mention again that there is a Hamiltonian here, that it's conserved. And you can rewrite your problem as eta, which is the original function that I mentioned, and c, which appears right here, thanks to the potential setup that we have. So they're going to have eta fc in our problem. And sorry, this went too far. Yes, here. And we can write the system in this format, if you like. There are two conserved quantity, the mass and the momentum. And let's look for a second at the linear problem in order to understand what kind of dispersion, for example, we have in this problem. And that we can do in this way. So if I define the function xc to be made by both eta fc, but I have to renormalize, I mean, they are presented with different kind of order derivative because the problem dictates that. Then I can rethink about the linear problem associated with the water wave as derivative of xc minus I, derivative order 1/2 c. And you can, once you know xc, this xc, you can write eta fc, because you can go back and write in this way. Okay, so that's the, so in other words, the eta is going to be a quarter derivative of this xc, and the psi is going to be minus a quarter derivative of this psi. Now, you can recast your initial data in terms of the initial data that I'm going to put for eta xc, and I'm going to write for you in this case. So, the initial data is going to be written again with these constants that are going to be fast decaying, like this. And then the alpha and omega and the beta and omega, by the way, different than the Schrödinger equation, the solution of the water wave are real valued function, not complex value function. So that's why it's written in terms of sine or cosine instead of the Euler notation that I had before for the Schrödinger. And for the dn, we have of course, we have to compare. Remember, the derivatives have to match in a certain way. So, but that's not really relevant for what I'm going to talk about later. So these are the initial data. Where is Alex? Okay. And then, as I say, once you have the initial data for psi and eta, and then you have also for xi, and I just wrote for you for precision, but it's not important for what comes next. Okay, so this is the main theorem, which I stated before with the H0 to compare with what the conjecture was. But the way of phrasing a little bit more precisely is with those initial data that I already wrote before, for any lambda greater than 0, a delta has to be for some technical reason in this range. And any k, think of k just to be an epsilon bigger than 0. And eta Tx is the free surface of our waterway problem with the data random data that I gave before, and then the large deviation principle actually tells us that this is what you should get, also for this highly nonlinear problem. And the most important thing is that it is exactly in the same range of time in which we know that there is a solution. And we don't know what happens, even deterministically, forget about random, but even deterministically, this is the range in which we can do it. Any question so far? Because now I'm going to start going through the proof. Okay.
Does it mean that even for very small time there could be very large crests for the profile?
But this is for all t.
Yeah, for all t.
Less or equal than that, you have this distribution.
So if t is very small,
Yeah.
is this estimate still true?
Yeah, for all t less or equal than this. The probability. Okay, so remark. This is not a phenomenal energy transfer. So if people working with turbulence, energy transfer in the sense of forward cascade, of growth to subwoolen norms or anything like that, the HS norm here doesn't grow. It's only the L infinity norm that we're looking at. This is also, so the initial data are Gaussian, but as I mentioned before, we don't know what happens later on in time, especially in this range of the size of the initial data, the -3. This also is not a problem in which you can use invariant measures, Gibbs measures, or things like that. And then the third point is something that I really wanted to stress. Alex talked about work that he did with Deng and Pusateri, and in which also using random initial data, they were in fact understanding the bound of the L infinity norm. And if you remember from Alex's talk, that bound of the L infinity norm is obtained in a set of measure, almost full measure. So the way to think about our result is the complement of that. Although Alex was talking a very large box or a large period, in fact there was this large L that he mentioned. In this case we are instead in a small period, but it is, I mean, it's not exactly a one-to-one relationship, but the way we think about it is that this is happening in the set that is missed by what Alex was talking about. So these are two complementary perspectives on a similar problem. Now, I hope I already emphasized for you that the main issue here is try to understand if we can have this synchronization of the phases, because that will tell me that basically the object that will give me the large deviation principle from the bottom, it's something that I can write in terms of the initial data somehow. Okay, so let me rewrite for you the eta. You can write in terms of some magnitude, and then there is this the cosine, right? The phase thing. This is a real valued expression because we have real value functions. Now let's. By the way, this everything in rho t, rho j, and theta j. There's going to be all the nonlinear stuff that happens. Okay, so I really have no control on that very easily, at least. And let's assume that we are an x equals 0. In fact, for the lower bound, it's enough that we understand what happens at a special point. Let's say 0 if you want. And now let's look at this set. This is exactly the set in which I have almost full synchronization of the phrases in a way. And before proving the main result, this is the main part of the theorem. It tells you that it is already in this. This was the event that you want to measure, but when we intersect already with this set in which there is synchronization, that we already obtain the large deviation principle. So basically, this tells us that at least the way we prove the result here, we are accepting, we are somehow proving this dispersive focusing event, that situation that happened. Between the two theories, we are accepting the first one. So this is the dominating effect, the fact that they align and they form the large wave. All right, what's the difficulty? Well, the flow map from my initial data to my solution is highly nonlinear, and certainly I cannot claim that this is anything that resembles anything that Gaussian. No invariant, quasi-invariant measures here, so I cannot use any of that to keep the dynamics under control. And the sharp lower bounds and the tails are hard to obtain when you have a long time. So this is the three things that this one tells me I cannot use Gaussianity. This is something that an object I don't have, and this just tells me that it's very complicated. So how do we start? Well, we would like to have some kind of an idea of how the solution looks like. And this is actually something that we know thanks to the deterministic, there is nothing random here, deterministic normal form reduction, okay, that already been, I will cite who did that in a moment, that already been used in order to construct some kind of resembling the nonlinear solution that I actually have. Then the second part, which is I had never seen it before in this context, is a probabilistic fixed point theorem, which tells me how I can actually prove that there is a quasi-synchronization of the phases. So let me explain a little bit more of both these two elements, which are the main part of the theorem. Now, the one about normal forms, okay, so I cite here some of the main people that worked on that, in particular the very recent work of Berti, Feola, and Pusateri. And this tells us that we can recast the problem that is in terms of eta and psi in terms of a different variable, let's call it zeta, by making a change of variable which is linked to normal forms. Now, this was done before, but in our theorem, there is an extra element that we need to prove. We need to prove that this sort of change of variable that takes me from the water wave problem with variable xi and, eta and xi into this normal form reduction, a new equation, which variable I'm going to call z. So this change of variable, which is highly nonlinear, is actually a Lipschitz in the proper topology. Now, I'm not sure how many people saw this normal form reduction, but basically you can write in the new coordinates the problem as dtz, and then minus I z bar on my Hamiltonian, now expressed in terms of z and z bar, and then this is the error that we have, which is quadratic. But this problem here is actually very nice, and will give us some nice expression for z. Okay. So what can we use? So this is purely deterministic, this argument, thanks to the previous papers that I mentioned. So there are some energy estimates. Don't worry about the order of derivatives here. This is not important. We're all going to work in L infinity norm eventually anyway. So this tells us that I have a good energy estimate. I can estimate the solution z in terms of the initial data. And then it's important that here we recall or we note that we have a fifth order power and then the t here. But the more important for us is the long time small data estimates that tells us if we start small, then the soup of this norm that we are working with is going to stay at most twice the initial data. And this is the famous time epsilon to the minus 3 that I have been talking about. So epsilon is time of the initial data and epsilon to the minus 3 is the time for which we can have these estimates. And like I said, there is some expression for this solution. So this can be written as e to the I, and then there is this really nonlinear frequency that we have up here. And then these are the transformed initial data. And then there are some error that comes from the fact that I'm doing the normal form, so there is the fourth power that shows up in there. Unfortunately, this expression is completely useless to us, because when we transform with this normal form coordinates, the initial data get all mingled together via this very high nonlinearity. So I have no idea what they look like, what kind of probabilistic property do they have. So this is not useful, and we're going to have to approximate this somehow if we want to do some probability. So we have to define our approximate solution, and how do we do that? So this is my z approximate. It looks very much like before, but this phase is the same bad phase that I had before, but now I'm going to take as initial data the original initial data, not the one transformed. And then I cross my finger and I hope that this stays close enough to what I want in the interval time epsilon to the minus 3 that I have. From the zeta, I can go back and write in terms of eta. There was a nice correspondence between the two. And my eta approximation is going to be the right number or derivative that you have to take, and this is z approximation. And now, does this work? So is this a good approximation for my original nonlinear surface in there? And we can say that actually this is possible. In the right interval time, the two are close in L infinity. And here is where the Lipschitzianity of that change of variable is going to have to be used anyway. So now I have my candidate, I have my approximate solution, and I need to make sure that I go back and do the probability for this guy, and I'm okay with that. And let's rewrite this in terms of the absolute values of my random data and so on. And all you need to think about it is, actually, I just noticed here that I should put, no, it's right. So what is this? Is my original very bad frequency, this one, which is highly nonlinear and so on. But then when I write my initial data, this one, in terms of radial polar coordinates, I pick up another frequency, this one. This is just coming from the initial data. This is from the nonlinear solution, and this from the initial data. And I wanted to align these frequencies somehow, say that they are basically all zero in a probability that is working for me. Okay, so now let's have set up the problem for this approximate solution. Now let me just go back to the upper bounds and then do the lower bounds as well. So now the first thing you have to do when you have to obtain, this is our goal, is obtain this upper bound, my large deviation principle from the top. Well, the first thing I have to do is make sure that I have solutions for this. So I have to make sure that my initial data in the right space are going to be small in the right way. And the complement of this event here, you can compute it, it's very easy, it's going to be negligible. So I will not worry, I will always say that I am sitting in this ball of initial data. I also record that when I evolve my, my problem with respect to eta and I subtract the approximation that seems more suitable for my calculation in L infinity norm, thanks to the energy estimate and so on, this is going to be close. You might lose a little k here, but in general it's going to be close in the basically right interval time, except for this k here, which is very, very small. So that tells me that I can, when I wanted to get a bound from above for this guy, I'm going to replace eta with the approximate eta. I'm going to lose a little bit because I have restricted myself to the ball. But at the end of the day, I'm going to end up with the same kind of estimate that I showed you at the very beginning for the Schrödinger equation. So this is going to work. And as I said, the upper bound is never really a problem. Now let's go to the more interesting fact. So now we are thinking about the lower bound for this problem. And as I said, the only mechanism that I have found so far that is working is synchronizing the phases. But this is highly nonlinear, this guy, so it's very difficult for me to think how I can do this. So let's fix x equals 0. So as I said in the example of the NLS, it's enough that you're taking the soup, so you're bounding from below, so let's fix x equals 0. And these are the type of frequencies that I want to synchronize. This is extremely nonlinear. This is coming from the initial data. Because remember, when I used the approximate solution, I used instead of taking all the initial data that had been scrambled together by the normal form change of variable, I'm taking the one I started with for real. So in order to synchronize, what that means is that I want that the cosine of this theta is going to be basically like 1. For frequency j less or equal to some very large n, what depends on epsilon. And then if I do that, if I'm in this good situation in which I can synchronize the cosines, then I can say that this, my approximate solution at x equals 0 is going to be basically of this form. So what is the probability that I can actually do this, that I can synchronize? Okay, so this is the new, somehow the new element, this is the fixed point idea. So what we're going to do is the following. So we're going to rewrite our initial data in which the first n frequencies, we are thinking of them not in a random way, but just as element of a certain vector field. So that's why I'm not putting omega here. So these are just phi j. So it's a vector, phi1, phi2, all the way to phi n. And then the remaining ones are the ones that are randomized. So this is, I'm going to put the tilde here because this is just, these are not random, this is just a vector put in there. And then, oops, sorry. Okay, decide not to work anymore. Here we go. Okay. So then I define the theta j now with this vector because I'm going to change it in a fixed point theorem. So this theta j is defined as what I had before, but instead of putting everything random, the first n are not random, as well as that. And now I'm going to define this, the operator tau, depending on this vector phi bar, which is this very nonlinear phase that I get as a solution of my problem. And what does it mean for the theta j to be aligned? Well, this means that the cosine of theta j is going to be 0. And then if the cosine of theta j is going to be 0, it means that this tau has to have a fixed point. I just want to remind you what is the cosine of theta. This I think is the sign not to. Okay. So if you think about this is the theta, this is my tau, and this is phi j. So if this has a fixed point with a minus in front, it means that theta j is 0. So that's why we think about the fixed point theorem. Okay. So aligning perfectly means that this cosine is 0, means that tau is a fixed point. And how do we do this? Well, there is actually a theorem. It's called we call it the random Brown fixed theorem. Why random? Because don't forget that this is only, the vector phi is only for the first n frequency. But from n on, it's random. So this is not a deterministic thing. And you can prove that indeed there is a fixed point. But this is probability 0. I mean, perfect alignment is probability 0. Does not give me the large deviation principle. So you had to make sure that if you are in a neighborhood of this fixed point, you are almost aligned, and that's good enough for you. And that's exactly what happens. So we need to say that if we give up a little bit on perfect alignment, we're just going to say we want the cosine of that quantity to be almost 1. Then we can see that there is a little neighborhood of the right measure around this fixed point, such that all those frequencies are going to be good for us. And that's how we write it. So we set now n alpha to be the set omega such that this phi j omega are close to my fixed point by an alpha. We know exactly what this measures is. We can calculate the probability of that. We have what we call a stability argument. So for any omega in here, the theta j that I wanted to be aligned, which I can write, as I said before, phi j omega minus this, stays small. And this is not going to happen for everything, but alpha small enough, this is going on, this is happening. And last thing that we need is what we call a factorized property. In other words, if I take A to be a measurable set in the sigma algebra generated by my initial data, the Rj and the frequency for j greater than n, so remember those are the ones that remain random, then the probability of the intersection of these two sets is going to be the product of the probability. By the way, this is not trivial because this A set is gonna, and the A and the N set are depending on this, so they're not independent a priori. So you really have to prove that. And now the last step of the proof. So we always are in this ball because we wanted the solution to exist, so you need to be small enough. Then I can take the event that I want to measure, intersect this ball, and basically this is the whole event. We say that the complement of B0 is negligible. Now, remember we are doing from below, so this is greater or equal. When we set x equals 0, we pick just one point. And we intersect with n alpha, which tells us that we are close to the fixed point. Now we use, if this we call this the event A, and I'm going to use this factorization property that I did before, so it's going to be the probability of this guy times the probability of this guy. And this is greater or equal than, well, this is exactly, since we have almost alignment, this is the bound that you get, just like for the NLS. And this is a little error that we make by assuming n epsilon, which is big enough. So this is the end of the proof, and that's a happy birthday for Sergio. I have to say, so a little disclaimer, when Scott gave his talk, the last picture was this beautiful cake that was going to, and I had the same. And then I said, so I got to invent another one, which I think is even better, because there is the light years, which is nice. Thank you.
Thanks.
Questions?
The first question is: do those solutions with large magnitude arise from extremely small solutions, or do they just remain of the same magnitude throughout time?
In what measure? In what norm?
In the infinity norm.
In the HS norm, they remain. Doesn't change much. By n infinity, well, we are measuring exactly that. What's the probability that they could grow?
Yeah, like with say for the if the initial data is of size epsilon initially, then does it grow to epsilon to the 1 minus delta after a certain amount of time?
More than in epsilon, we measure in terms of, well, you want to measure in terms of its z0. That's what the large deviation principle tells you, not in terms of epsilon itself.
Okay.
So that's the statement of large deviation principle is that.
And my second question is, if we do not make that vertical normal field transformation, can we obtain the same type of result just with a smaller time scale?
Okay, so if we don't do that, I guess the other way that I know, and maybe Alex can help me with this, of saying that there is a solution is energy method. And I don't have any kind of expression for the solution in that case, as far as I know. So here the transforming into a normal form just gives you an expression for the solution itself. That helps. But whether there is another way of doing this, I don't know.
But the linear approximation functioned well up to the
yeah, exactly. Totally. I totally agree with you. For a smaller interval of time, you can take the linear approximation, which I mentioned before. But that's kind of, it's going to be short. Yeah, but you're right.
So if I understand correctly, you consider the water wave problem on infinite depth because you have a good idea what to do with NLS. Does it make sense to?
Maybe we also have a good idea of what are the results. Where is Alex that I gave? Now I don't see him. Alex, yes. Also, it depends on what do we know for the problem deterministically in terms of solutions and how we can represent it.
So my question would be, is there any
what do we know for the finite depth, Alex? In periodic.
It's almost the same, I would say.
Almost, but is it written?
No, but you don't get the epsilon the minus 3 times.
Yeah.
Epsilon the minus 2 times.
Yeah. So then probably, yeah. Modulo that, then I believe this can be repeated. Yeah.
Maybe even better because it is finite depth, then you have better control for the resonances.
But we don't use resonancy control here.
Make the normal form transformation.
Ah. Yeah, I don't know. I have not done the calculation for that.
So I presume that this is sort of a general thing, right, that could be applied to many other nonlinear equations.
Yeah, where it makes sense to think about this question, right? Like the
you
magnitude where it grows. Yeah.
Say it always makes
Yeah.
sense, and it's theoretically,
Yeah.
whether it has an
Yeah.
application or not.
Yeah. I think to me now there are two interesting questions. One, higher dimension, and two, what happens beyond this epsilon to the -3. So that's,
is there any theory for that? I mean,
I don't know. There are
large deviations that goes beyond.
The people have told me that there is some kind of stuff that will start coming from the more resonant parts, from the part that we ignore in the normal form reduction, the extra terms that maybe they start kicking in and doing stuff. So maybe we don't have this principle there, but we don't know. I don't know if there is a conjecture.
Can one make an experiment to see how the theorem applies? I mean, to count
there are people working on tanks and doing things. That one of the pictures that I put at the beginning is exactly that. But
I think multi-dimensional tanks is more complicated because I think there have been experiments with two different trends of
like a solid tones more.
Weird pictures.
Yeah.
Other questions? Yes? If no more questions, let's thank the speaker.
Thank you.